I'm going to go through an example of a stoichiometry problem and try to point out some important principles here that you should keep in mind when you're solving these problems. As an example, I'm going to use the reaction between iron 3 oxide and carbon to form elemental iron and carbon monoxide. This is an example of, in fact, how iron is often made from iron ore. You mix it in with carbon, you burn it at a very high temperature, and the carbon reduces the iron 3 oxide to elemental iron and also produces carbon monoxide as a byproduct. So the point of this is that we have these stoichiometric ratios that give us the ratios of the moles, not the mass, but the moles of different substances in the reaction. So in this case, some few examples, there are 3 moles of carbon monoxide that get made for every 1 mole of iron 3 oxide I start with. There are 2 moles of iron that are made for every, say, 3 moles of carbon monoxide that are made, or one other example that you need 3 moles of iron to make, 3 moles of carbon to make 2 moles of iron. The point is I can relate any 2 substances in the balanced equation to one another, either on the same side or the opposite side of the arrow. The point is, though, these relationships are always mole relationships. So, for example, if somebody asks you how many moles of carbon are needed to react with, let's say, 4.6 moles of iron 3 oxide, then I solve that by using a simple mole-mole ratio. In other words, I've been given 4.3 moles of iron 3 oxide, and the ratio is 3 moles of carbon are needed for every 1 mole of iron 3 oxide. I see that in the chemical equation, and that'll work out to 13 moles of carbon. In other words, the calculator, notice, said 12.9, and I round that to 13, 2 sig fig number, given that I was given 2 sig figs, the 4.3 is my given. Notice the 3 moles to carbon to 1 mole of iron 3 oxide is exact. All stoichiometric ratios are definitely exact. In part B, I might ask how many moles of carbon monoxide do you get from 18.0 grams of carbon and excess iron 3 oxide. We'll look later at the idea of a limiting reactant problem. So the point is, I want to know how much of product I get given a certain amount of one reactant, and we just assume you have plenty of the other reactant. We can think in terms of extremes. If you didn't have any of the other reactant, then you wouldn't have any product. So we have to assume you have plenty of the other reactant. Now notice I gave you 18 grams of carbon in this case. You have to pay attention to the units you've been given. If I have 18 grams of carbon, the first thing I have to do is use the molar mass of carbon to turn that into the equivalent number of moles of carbon, which is 1 mole of carbon is 12.0 grams of carbon from the periodic chart. Then I apply the ratio that it's 3 moles of CO for every 3 moles of carbon. Notice this ends up being a 1-to-1 ratio, which means you could really avoid using it in the calculator, but you have to write the ratio down. There's always a stoichiometric ratio between substances. And so arithmetically, this works out to 1.5 moles of CO. Notice I gave you mass of a reactant, and I wanted to know the moles of the carbon monoxide. You have to notice the units. Now, it's probably more conventional to ask a question that always has to do with grams. For example, how many grams of iron do I expect to get from 31.0 grams of carbon, and again, excess iron 3 oxide? So notice here, carbon doesn't even appear in the formula of the iron, clearly, but you have to have carbon in order to make iron from iron 3 oxide. If you run out of something, any reactant, then that stops the reaction. Also notice I'm giving you grams, and I want to know the answer in grams, and that means there'll have to be here 2 conversion ratios. In other words, involving molar mass. I'm starting with 31.0 grams of carbon, and the first thing I find out is how many moles of carbon is that. It's 12 grams of carbon, or 1 mole of carbon over 12 grams. I've set this up so the 12 grams of carbon, the grams of carbon, I should say, cancel with the grams of carbon. Then I look to find out what the molar ratio is. Well, it's 2 moles of iron for every 3 moles of carbon. That's what notice now at this point, the moles of carbon have cross-canceled. Then finally, when I look up on the chart, it says it's 55.8 grams of iron for 1 mole of iron. And that arithmetic comes out to be 9.61 grams of iron. Notice in this case I'll be dividing twice by the numbers 12 and 3 under the fraction bar and multiplying the twice by the 2 and the 55.8. So the way I run this through the calculator is I type in 31.0, then I'll go times 2, times 55.8, divide 12.0, and then again divide 3. And that comes out to 9.61 grams of iron. The general trend here is in these full stoichiometry problems is you start with a mass of one thing, in this case, say the mass of carbon. You find out how many moles that is, and you always end up using the molar mass upside down to do that. Then you turn the moles of the one substance you're starting with into the moles of whatever you're being asked about. That's what the molar ratio is for. And finally, the moles of the second substance, if necessary, are turned into the mass of the second substance. It's always exactly the same pattern in working out these stoichiometry problems. And you want to make sure you understand the pattern. Once you've done it a couple of times, and there are plenty of examples, then I think in the book, I think you'll find it's not difficult at all.